Welcome back, 6th grade. Today we are doing Investigation 9. Well, as you know, investigations, usually we have these worksheets that we do together, and we are going to do that again, except this time it's going to be through video. So I have left the worksheet for you to either print out at home, or you can go to the school and pick one up. They are left on a pillar for you to pick one up outside of the school, and I have a picture of where that is for you to pick one up. If you're not able to print one or pick one up, you can do this along with me on a piece of lined paper. When it is completed, I will need you to upload the picture and attach it when you click on the I am done button. So do this with me and show me that you've completed it, and hopefully you're able to pick one up or print one. But if not, you can do this on lined paper. And then you're going to take pictures of all of the pages and show me that you've done it with me. So let's get started. Investigation 9, we're graphing functions. Now remember that a function is a rule. A function is a rule that tells us the relationship between two numbers. And if you remember, we had our function factory, right? Our function factory where we had something that goes in, something that happens inside, and we get something that comes out. So if this was our function factory over here, y equals 2x would be what's happening inside of our function. Okay, and our rule is y equals 2x. So every time that our x is 0, our y would equal 0, because 2 times 0 equals 0. Every time our x is 1, our y would equal 2, because 2 times 1 is 2. Every time that our x is 2, our y would be 4. Every time our x is 3, our y would be 6. And so these can give us coordinates for us to then plot over here on a graph. You can see that our x and y give us these coordinates. Now, these are just a few possibilities for x and y. But if we plot just these 4 coordinates, we can then make a whole line and we can see all the possibilities for x and y. And you can see they go on forever in both directions, right? We don't want to make a table of all the possibilities because there's an infinite number of possibilities. But this line, this graph, shows us all the possibilities for this rule of y equals 2x. It shows us every xy pair by drawing that line. So moving on, here is a graph of the relationship between side lengths and perimeter of a square. So instead of x and y, they're giving us p for perimeter and s for side length. So to kind of give you a visual here, side length for a square and then perimeter, right, would equal 4s, right? So I take this side and I multiply it by 4, because side. So 4s gives me my perimeter. So that's how they've come up with this function over here. So if I had a side length of 1 times 4 gives me a perimeter of 4. 2 times 4 gives me a perimeter of 8. 3 times 4 gives me a perimeter of 12. And then they can take this SP and they've graphed it over here. The coordinate 1, 4, the coordinate 2, 8, the coordinate 3, 8. Now, notice something here. I'm right here at 0, 0. Okay, because if I had a side length of 0, I would have a perimeter of 0. There would just not be a square, right? So this becomes a ray and not a line. The function we had before was a line, right? It went all the way through. Notice this one is just a ray. It stops right here. So our answer over here for the graph of this function is a ray. What are the coordinates of the endpoint of the ray? Our coordinate for the endpoint of the ray is 0, 0. Why is this graph of this function a ray and not a line? Well, if the graph were a line, there would be negative numbers for the length of the side of the perimeter. Well, we can't have a negative side. That's not possible, right? We can't have negative numbers over here on our side. So there would be negative numbers for the length of the side and for the perimeter. And lengths cannot be negative. Okay. The graph of the function p equals 4s is a straight line and not curved. Below are two squares. The side lengths of the larger square are twice the side lengths of the smaller square. Well, let's see. 2 centimeters, 4 centimeters. Yep, 4 centimeters is twice 2 centimeters. Find the perimeter of each. Okay, so our perimeter of our 2 centimeter square, well, 2 times 4, or 2 plus 2 plus 2 plus 2, that gives us 8 centimeters. And then 4 plus 4 plus 4 plus 4, or 4 times 4, gives us 16 centimeters. What effect does doubling the side lengths of a square have on the perimeter? Well, notice this. We doubled the side lengths, and our perimeter also doubled. 8 times 2 is 16. 2 times 2 is 4. 8 times 2 is 16. So as we doubled our lengths, our perimeter, doubling the side lengths, doubled the perimeter. Okay, so for number 3, they want us to do what we just did for a square and now do it for a triangle. And they want us to come up with a function, fill in the table, and then create a graph. So let's think about it. We have our triangle, and we know we have side, side, side. So our perimeter would equal 3 times s. So we can put 3 right in there. So if I have a side of 1, my perimeter would be 3. 1, 3. If I have a side of 2, well, 2 times 3 is 6. So then 6 would be my perimeter. If I have a side of 3, 3 times 3 is 9. So then 9 would be my perimeter. So now that we have our coordinates, we can come over here and we can graph it. So we first find our 1 for our side, 1, and then we go up to 3, and then we can graph it. Then we find our 2, and then go up to 6. Our 2, go up to 6. Then we find our 3 and go up to 9. 3 and go up to 9. And then you take your ruler and you connect the dots. I don't have a ruler with me, so I'm going to do the best I can. But if you do have a ruler, I'd like you to use it. But I don't have one, so I'm just going to do the best I can here. And that is my very ugly line, but you get the idea. Okay, so you should have something that looks like this on your paper. Okay, so moving on, rates are also functions that can be graphed. And we have worked with rates when we've talked about speed and distance. So here's an example of one. Sam enters a walkathon and walks at a steady rate of 3 miles per hour. So that 3 miles per hour is a rate. And we've worked with these types of rates in the past. And we can put this rate into a function table. If he is been walking for 1 hour, then he's been going 3 miles. If he's been walking for 2 hours, then he's gone 6 miles. 3 hours, he's gone 9 miles. And then we can take this function of hours and distance, and we can graph it. And the cool thing about graphing it then, especially when you see that we've spread these hours apart, you can see exactly how far he's gone even in between the hours. Notice, and it says it right here, notice that each tick mark on the horizontal scale represents 1/4 of an hour. So we spread these out by 15-minute increments. So you can even see how far he's gone every 15 minutes by looking at it at this scale, the distance. Okay, so you can see that every 15 minutes, you know, how far he's going, and how far how long it takes him to go 1 hour or 2 hours or 3 hours or 4 hours, and not just 1 mile or 2 miles, how long it takes him to go 1 mile or 2 miles or 3 miles or 4 miles, and not just that 3, 6, 9. But you can see how long it takes him to go each of those by graphing the entire rate. Okay, so now here we get to do one ourselves, and the question says, Sam entered a jogathon and was able to jog at a steady pace of 6 miles per hour for 2 hours. Write an equation for the 6 mile per hour rate, then complete the table. Okay, so he jogged at 6 miles per hour. So his distance was, distance equaled 6 times hours. So if he went for 1 hour, then his distance was 6 miles. If he went for 2 hours, then his distance equaled 12. 2 times 6. Okay, so then we go down to the graph, and you can see that they already did the first one for you, right? 1, 6, and now we have to go 2 up to 12. And then connect the dots so that we can see his total rate. There we go, that's a much better graph this time. And now you can see all of his rate for the entire thing, and notice how each of these tick marks represents 10 minutes. Okay, so now we're going to do 5, 6, and 7, and I went ahead and pulled in a digital copy of the graph we just made, because I want us to refer to the graph that we just made to find the distance Sam had jogged in 40 minutes. Well, this is very small, so you're going to want to refer to the graph you just made, because it'll be easier to see. But if you want to find out the distance he jogged in 40 minutes, remember that each of these tick marks represents 10 minutes. So you go over 4 tick marks and then go up and see where it matches. And you should see that it matches right at 4 miles. So you're going to write in 4 miles. Then it says, refer to the graph to find how long it took Sam to jog 9 miles. So now we want to go up to the graph and say, okay, well 9 miles is that tick mark in between the 8 and 10. And I want to follow it over here and then see how long it took. And on your graph, it's easier to see than this one. And hopefully you're seeing that it took 1.5 hours. And then our last question, why is the graph of the distance Sam jogged a segment and not a ray? Sam did not what forever. He stopped after what hours? Okay, so over here, I did kind of make a mistake because I wasn't paying attention. Remember it said that he had a steady pace of 6 miles per hour for 2 hours. So I kept this going, and I guess I should have stopped it right here. I should have stopped it right there. So you guys can fix that on yours to match this right here. Because he did say that he stopped after 2 hours. He did not jog forever, right? He did not jog forever. He stopped after 2 hours. Okay, so now we're going to talk about direct variations. Direct variation is a relationship between two variables in which an increase in one is a proportional increase in the other, or the opposite. A decrease then is a decrease in the other. So here's an example of a direct variation, and this is something that we see all the time, and you might see this with your chores at home, or when you start working, and your parents can attest to this. The longer that you work, the more you get paid if you're working hourly. The less you work, the less you get paid. The two pairs of numbers will follow the rule of the function. So in this case, let's say if you work 1 hour, you get $5. If you work 2 hours, you get $10. If you work 3 hours, you get $15. And if you work 4 hours, you get $20. Maybe some of you babysit, and you have seen this when you babysit. If you if you work an hour of babysitting, you get $5. Maybe you've seen that, something similar to this. Okay, this is called a direct variation, whereas one increases, the other one increases. Or as one decreases, the other decreases. Now there's actually a very specific formula that we use for direct variation. It's called y equals kx. And this formula is our direct variation formula. Okay, now you recognize the y and the x. This k right here stands for constant. Constant. If you remember from a few weeks back, we talked that our constant never changes. Our constant never changes. Okay? So if we were to make our function into a formula that looks like this, our y is, well, how much money we're going to make, and our x is how many hours we've worked. So this is, let's use a different color over here. So this is the hours that we've worked, or excuse me, the dollars that we've made, and then x is how many hours we worked. So we can fix these colors over here too. So let's look at this. If I work X amount of hours and I get Y amount of dollars, well, it looks like it's going up by 5s. So my constant in this particular case equaled 5. So Y equals 5x. This should look familiar to you because when we did our other examples, we had direct variations. Remember, over here, D equaled 6y. That looks a lot like our y equals 5x. Remember, D equals 6y. Well, we could make that y equals 6x, right? It's the same setup. It's the same setup. It's a direct variation. As one increases, the other increases. As one decreases, the other decreases. Another way you can know that this is a direct variation is through cross products. So look here what they did. They took a 2 and a 10, the 2 and 10, and the 3 and 15, the 3 and 15, and they did cross products. Well, 2 times 15, does that equal 3 times 10? Well, 30 does in fact equal 30. Let's try another one. Let's try 1 and 5, 4 and 20. So let's see if 1 over 5 equals 4 over 20. We take the cross product, 5 times 4, and does that equal 1 times 20? Well, 20 does equal 20. So the cross products are the cross products of the proportion equal. Yes, they are equal. And so that proves, again, that's another way to prove that this is a direct variation. Okay, so let's talk more about this direct variation. They give us a question here, question 9. Circle the letter of the one that is not an example of direct variation. A, the length of the side of a regular hexagon and the perimeter of the hexagon. Okay, so as the length of the side increases, does the perimeter increase? As the side increases, does the perimeter increase? As the side decreases, does the perimeter decrease? Yes, it does. So this would be a direct variation. Number of books in a stack and height of the stack. Well, the number of books increases, would the height increase? As the number of books decreases, would the height decrease? That would be true, so this is a direct variation. Okay, speed at which you travel to school and time it takes to get to school. Okay, so as your speed increases, would the time it takes to get to school increase? As your speed decreases, would the time it takes to school decrease? Gotta think about that one. Let's come back to that one. The length of a segment in inches and its length in centimeters. Well, if my inches increases, then my centimeters would also increase. If my length in inches decreases, then my length in centimeters would decrease. So that is a direct variation. Okay, let's come back over here. Speed at which you travel to school and the time it takes you to get to school. Well, if you're traveling fast, then usually your time is going to decrease, right? If you're going faster, then it's going to take you less time to get to school. If you're traveling slow to school, then it's going to take more time to get there. So this one here, the speed at which you travel to school, is not a direct variation because as one is increasing, the other is decreasing. So this would be your answer. C is not our direct variation. So then let's move on. The graph of a function with direct variation is 1, a straight line, slopes upward to the right, and must include the origin. Okay, so when we're graphing a direct variation, it has to include those three things. Okay, it has to be 1, straight line. It curves up, or excuse me, the slope is up to the right, so up and right, and it has to have the origin in it too. Okay, this is very important to remember. Our direct variation graph has those three things. Very important to remember. So out of these 4 graphs, which one is a direct variation? Okay, well first it has to have a straight line. So we can say that this one is not a direct variation. Okay, then it has to go up to the right, up to the right. So we can say that this one is not a direct variation. Then it has to include the origin. Well, this one does not include the origin. So this one is not direct variation, which means A is our direct variation. Straight line, up to the right, includes the origin. So graph A is an example of direct variation because the graph of the function is straight, slopes upward to the right, and includes the origin.